Hello, example 1-4 is about sluice gate. So a sluice gate in the rectangular channel is installed to control water level downstream of the channel. In this example, a sluice gate is installed in a 2.5 meter wide rectangular horizontal channel as shown in this figure. And then we have the water depths in the small distances upstream, which is at section 1, and downstream at section 2 of the gate, which are 2.75 meter and 0.25 meter or 25 centimeters. So here y1 is 2.75 and y2 is 0.25. So knowing the fact that we have y1 and y2, we would like to estimate the discharge in two conditions. The first condition is by neglecting the energy losses. So assuming that energy losses is 0. And in part B, we assume that the energy loss at the gate is 10% of the upstream depth. So it's equivalent of 10% of the upstream depth. And then in the note section, the water depth downstream of the gate is smaller than the gate opening A due to flow contraction. So what we use is the depth at y1 and y2 instead of the actual opening. And the relationship between the opening and y2 is normally y2 is 0.61 times of A. So once you calculate y2 and you want to know what is the gate opening, you can divide it by 0.61. So we start with energy equation for rectangular cross section. So in part A, energy equation for rectangular section. For rectangular cross sections, I can combine energy equation with the continuity equation. So we know that V is equal to Q divided by Y, and Q is a specific discharge. So that's a continuity equation. And then I can combine that into energy equation. So I'm going to have Y1 plus Q squared divided by 2G y1 squared is equal to y2 plus Q squared divided by 2G y2 squared plus energy loss. So in part A, we assume that the energy loss is negligible, so it's going to be 0. And then we put the values for y1 and y2. So 2.75 plus Q squared divided by 2 times 9.81 times 2.75 square is equal to 0.25 plus Q squared divided by 2 times 9.81 times 0.25 square. So we have one equation, one unknown. So you can rearrange the equation. So basically we have 2.75 minus 0.25. And then you can multiply both sides by the denominator. And then at the end, you will get times 2 times 9.81 times 2.75 square times 0.25 square is equal to 0.25 square Q square plus 2.75 square Q square. Okay. And then if you calculate the left-hand side, you will get 23.18 is equal to 7.625 Q square. And from that, you can calculate Q is equal to 1.74 cubic meter per second per meter. Okay, now if you want to calculate the total discharge, then total discharge Q is equal to the specific discharge time width, which is 1.74 times 2.5, and gives you 4.35 cubic meter per second. So that's part A, when we assume that the energy loss is negligible. So we go to part B, where the energy loss is actually equal to 10% of Y1. So then we have Y1 plus Q squared divided by 2G Y1 squared is equal to Y2 plus Q squared divided by 2G Y2 squared plus energy loss. So for energy loss, I use 0.1 Y1. Okay, so same as part one, you have all the known values except discharge. So we can replace all the values, 2.75 plus Q squared divided by 2 times 9.81 times 2.75 square plus Y2 0.25 plus Q squared divided by 2 times 9.81 times 0.25 square, and then plus energy loss, which is 0.1 times 2.75. Okay, so one equation, one unknown, and you would be able to solve the specific discharge in this case. So we have Q is equal to 1.65 cubic meter per second per meter. And from that, total discharge is Q times B, which is 1.65 times 2.5. And it becomes 4.14 cubic meter per second. Okay, so if you compare the answer without any energy loss with the case that we have energy loss, you'll see that actually the energy loss reduces the discharge. So the more you have the energy loss in the system, it basically allows to have less discharge going through the hydraulic structure. Okay.